sat in the back yesterday because every time I come in after he starts like bump the camera, knock it over. And I watched the recording. I'm like, yeah, that was
All right, guys. Yesterday we introduced reactions that we can do with alkyl halides, and we started by looking at elimination reactions. I gave you a generic elimination, is that right? I said, generically, you take this this alkyl halide, X, with a neighboring H, and you react it with some base, and you get an alkene. But that's not the only elimination reaction that alkyl halides can go through. Because if you have a dialkyl halide, and it's tough here because there's two forms that this can happen in. You could have a geminal dihalide or a vicinal dihalide. And if you react this with a very strong base and heat, then you can actually run a double elimination, right? And both of these actually give a specific intermediate. They run through an elimination just like the formation of the alkene, but only one of the X's and one of the H's get removed. Then a second elimination removes the second H and the second X, the second halide, and gives us our final alkyne. So there really are two eliminations, two types of eliminations that alkyl halides can go through. Elimination to alkenes and elimination to alkynes. And then we said that under elimination, there's E1 versus E2. First order elimination and second order elimination. What's the main difference between the two? So the type of base? True. Yeah. So the main difference, the difference in their name, 1 and 2, is how many compounds determine the rate of the reaction. How many compounds will impact how quickly product is formed. But that rate difference depends on the type of base. So we said that we have weak bases that run E1, and we have strong bases that run E2, and then we said that there were small strong bases and there are bulky strong bases. Of these three classifications of base, weak, small and strong, bulky and strong, which are predicted to give the most stable product? Bulky? Weak? What word do we describe for the most stable product? What word do we use to describe? Or whose name do we use to describe the most stable product? Zaitsev. So similar to Markovnikov, we're the most stable carbocation intermediate forms. Here, Zaitsev says the most stable alkene forms, which is the most substituted alkene. An E1 mechanism proceeds by a carbocation intermediate. that intermediate can react in a lot of different ways. It's going to react through the smallest activation barrier. So this always gives a Zaitsev product. But the bulky, sterically hindered base, this experiences far too much energy strain to get at the most substituted carbon and give the most substituted alkene. So the bulky base gives us anti-Zaitsev, and yesterday I gave you another name that you might hear in some places. Whose name was that? Hoffman. Missed the boat. He got there too late, and Zaitsev already got anti-Zaitsev named after him. Oftentimes, Hoffman elimination is used in specific contexts, like when amines are leaving groups, which is not very common. Then we look at our third condition, the small, strong base. Now, E2 reactions don't just have stereochemistry involved, they are stereospecific. We're going to look at what that means today, which means, if possible, the small, strong base prefers Zaitsev, but it's not always possible. Sometimes the stereochemistry doesn't line up for it. All right, so we're going to look at a few examples, and then we're going to move on to look at mechanisms. All right, 1-bromo, 2,3-dimethyl cyclohexane. I'm going to react this in 3 different conditions. In the first condition, I'm going to add water and heat. Delta there, that triangle, indicates heat, just providing energy to the reaction. In the second condition, I'm going to add hydroxide and heat. What is the difference between water and hydroxide in terms of their effectiveness as a base? Sorry? Hydroxide is a better base? I'm throwing you off. Water is a better base? Now I'm throwing you guys off. How can you use charge to compare the basicity of the two? Do you remember section 2 very early on? No, was that section 1 very early on? We used Careo to compare acids and bases. More negative charge, typically more basic. Hydroxide, better base than water. All right, in the last condition, I'm going to use tert butoxide. Can someone describe the substitution of my alpha carbon? We're going to refer to this carbon that has the halogen as alpha. This is a point of interest. Remember we talked about alpha cleavage back in mass spectrometry? That's our alpha carbon. What is the degree of substitution of my alpha carbon here? Secondary? Tertiary? Yeah, we consider bromine here to be a leaving group. It's going to leave the molecule. Is that a secondary alpha carbon or a tertiary? Maddie, do you want to try and defend what you said?
I thought it was tertiary.
Oh, up there maybe.
Oh, sorry, we're looking down here.
In this example,
Oh, well then.
What would you say?
That was a secondary.
Why is this a secondary alpha carbon? That carbon is bound to 2 other carbons. What is attached to alpha is called beta, and this is where the hydrogens are. So we look at the beta hydrogens in elimination reactions. How many beta positions are in this molecule? If it's a secondary alpha, then there are 2 beta positions. Primary alpha has 1 beta position. Tertiary alpha has 3 beta positions. The number of beta hydrogens, well, sorry, that's a step too far. The number of beta positions is equal to the substitution of your alpha carbon. So talk to me about this beta position. Are there beta hydrogens? Yeah, CH2, 2 beta hydrogens. What's the degree of substitution of that beta position? Sorry, I beat you to it. Secondary. It's a CH2 group. That carbon's bonded to 2 other carbons. What about my other beta position? What is the degree of substitution at the second beta position? Tertiary. You guys would agree that this is the other beta position? What we're going to form is an alpha-beta double bond. The more substituted the beta carbon, the more substituted the alkene. The less substituted the beta carbon, the less substituted the alkene. Zaitsev gives the most stable, most substituted alkene. Anti-Zaitsev, less stable, less substituted. So on my anti-Zaitsev product, which alkene should I eliminate, or sorry, which beta carbon should I form the alkene with? Least substituted beta. So here's the product that I get with tert butoxide. That's 3,4-dimethyl cyclohexene. Tert butoxide has eliminated a hydrogen from the least substituted position. Hydroxide, on the other hand, wants to go for the most substituted beta position. So hydroxide gives me 1,6-dimethyl cyclohexene. Hydroxide has eliminated from the Zaitsev position the most substituted. Do you think that the product with water will be the same as either of these other 2 or unique? First, we have to recognize the difference in the mechanism. H2O is going to run an E1 reaction. This is E2. This is E2. This is E1. E2 does not have carbocation intermediates. So only adjacent beta positions can give alkenes. E1 has a carbocation intermediate. And what's possible with carbocations? Rearrangements. But only rearrangements if there's a more stable carbocation that could form adjacent. Secondary carbocation, adjacent to a tertiary carbon, hydride shift creates a tertiary carbocation. So I'm going to redraw that tertiary carbocation because now my alpha and beta positions have switched. Or not necessarily switched, but they've changed. All right, hang on. I'll give you a step back. This is the carbocation that forms when the alkyl halide breaks off. This is the carbocation that forms after the rearrangement. What is the substitution of that carbocation? Raise your hand when you know the answer. No need to say it just yet. 2 of you, 3, 4, 5, 6. What is the substitution of that carbocation? You guys are good. How many carbons is that carbocation carbon bonded to? Tertiary. It's bonded to 3 other carbons. So how many beta positions are there? Good. Tertiary alpha has 3 beta positions. What are their substitutions? Somebody give me one of the substitutions of a beta carbon. Carly? Where? Down here. Somebody else. Oops, sorry, that's beta. Where's the tertiary? To the left. Yeah? You said the methyl.
I was saying the 3.
Here?
Yeah.
That's tertiary? What is that?
Well, I used to there was the amount of hydrogens.
No, the degree of substitution
Oh.
always is number of carbons. That's primary up here. And this is a tertiary beta. Are you guys okay with this idea that we have scoped out the alpha carbon? By knowing its degree of substitution, we know how many beta positions exist, and then we just describe the beta positions. Where will the most substituted alkene form? Between the tertiary alpha and what beta? The most substituted, the tertiary beta. So the product that forms, well, let's just check quick. Are there beta hydrogens at each of those positions? Yeah, there's 2 beta hydrogens here, 3 beta hydrogens here, and 1 beta hydrogen here. So I can form an elimination there. It doesn't work if there's no beta hydrogen. So here's the product of the elimination with water. Tell me what you notice about that top product compared to the starting material. Just reiterating what we already know. The original alpha carbon is not involved in the alkene. There has been a structural rearrangement that has occurred. These bottom 2 positions, the original alpha carbon is involved in the alkene, but in the top product, the original alpha carbon is not. That is your strongest evidence of a carbocation intermediate. That is your strongest evidence of an E1 mechanism. Deal? You can't have a structural rearrangement without a carbocation, and you don't have a carbocation in E2, so this must be an E1 mechanism. All right, let's look at these mechanisms. What method do you guys prefer? Step-by-step mechanisms or fully sequential mechanisms? Step-by-step? If you're not a fan of step-by-step, then all you have to do is just show all of the arrows connecting all of the intermediates. You don't have to show the intermediates first. First step. Leaving group leaves. Sorry, I usually like to put that in the name. First step. Leaving group leaves. What is my leaving group? Bromine. I'm going to draw water in here. It's not going to play a role yet. First step, leaving group leaves. I produce a carbocation and bromide. How easy do you think that is for that leaving group to just leave and create a carbocation? Very easy, rather difficult. Does that take a lot of energy, or does that happen pretty quickly? That takes a bit of energy. That is the rate determining step. Once that intermediate forms, the rest of the reaction happens very quickly. Step 2, Step 1A, because this is not always true of all E1 mechanisms, hydride shift. This is only true in mechanisms where a carbocation rearrangement occurs. Carbocation rearrangements don't always occur. In this step, I'm actually going to explicitly draw out the beta hydrogen on that tertiary beta carbon. And my hydride shift is as easy as showing that beta hydrogen taking its electrons to the carbocation. In its wake, it leaves behind a new carbocation. Are you guys okay with me calling that step 1A? Because it doesn't always occur in all E1 mechanisms. It's not like it's a step you can count on. It's a step that only happens if it's possible. There's two ways you might think of this final step. You might think of it as deprotonation, because this is where the carbon will lose its hydrogen. Or you might think of it as elimination. It's maybe better to think of it as deprotonation because it tells you what needs to happen. When I draw this, I'm going to explicitly show the beta hydrogen that is being eliminated. I have to explicitly show that beta hydrogen because it needs to be deprotonated. I need to break its CH bond. Okay, question for you on acidity. What's a better base, Br minus or H2O? Raise your hand for Br minus. Maybe half the class. Raise your hand for H2O. Oh, very few. Okay, question. What is the pKa of HBr? It's like -5, -7. What's the pKa of hydronium, H3O+? -3 or -2. What's a better acid, HBr or H3O+? HBr, it's more negative. What's a better base, H2O or Br minus? H2O. So I'm going to give you two options. I'm happy for you to show the bromide acting as the base because it's not implausible. I'm also happy to let you show the water acting as the base because that is much more likely. Both of them are acceptable. In fact, there are instructors, people who show mechanisms that say you don't need to have a base shown here. You can just have hydrogen ion float away, nothing bonds to it. That's not possible, but it is kind of an assumed way of showing things. What would you guys like to see? Bromide or water as the base? You want to see what's more likely, even if it feels a little bit weird in terms of stoichiometry? Let's do it. H2O bonds to water. CH bond breaks. Who owns the CH bond? C. More electronegative. What is C going to do with that excess electron density? It's going to share it with its neighbor who is electron deficient. Carbon-carbon double bond forms. Plus, I get Br minus and H3O plus as byproducts. 1,2-dimethyl cyclohexene is formed. Do you have questions on that mechanism? All right, mechanism for the Zaitsev E2. Step 1, deprotonation and leaving group. I need to explicitly show the CH bond because, as you can see in the name, there's one, the deprotonation happens here. Hydroxide, in this example, was serving as my small base. Could have used a number of other small bases. Hydroxide takes the beta hydrogen, CH bond, comes down to form the carbon-carbon double bond. Yikes, that's breaking the octet at the alpha carbon. So that carbon needs to lose a bond. Needs to lose the CBr bond. Who takes the electrons when the CBr bond breaks? Bromine. Let's pay attention to everything that has just happened. Carbon-hydrogen bond breaks. Carbon-bromine bond breaks. Carbon-carbon double bond forms. There's your E2 mechanism. Do you like that or not? Why do you like it? One step. That's it. No rearrangements, nothing. Just one step. I think that's pretty nice. Let's look at the mechanism for anti-Zaitsev E2. How many steps do you think this will be? One? Why? Because it's still a strong base and it's just happening at a different carbon? You'd be exactly right. The deprotonation and the leaving group, leaving happens at the same time. The only thing that I need to pay attention to now is where. Here's my tert butoxide. There's a lot of different ways to write tert butoxide. TBuO minus, this little O- with a chicken foot off of it. Or you can do its condensed structure, OCCH3. I want you to be comfortable with all of them. Terbutoxide goes for the least substituted beta hydrogen. CH bond breaks. CC double bond forms. And the CBr bond breaks. One step. Regiochemistry is important. I form tert-butanol in the product and bromide. Okay, there's one small thing that I want to mention. It might not always be written over the reaction arrow OH- or TBuO-. Sometimes you have a counter ion that's shown on the reaction arrow, but it is literally a spectator ion. It doesn't play a role in the chemistry, it just balances charge. So here, there may very well be a sodium ion that is floating around, and that sodium ion then balances the charge of bromide. One thing that I have seen OChem 1 students and OChem 2 students give me is this as a starting material. And they'll start by showing the NaOH bond breaking. Stop it. Stop. Why are you doing that? What is that bond? Describe it. A cyclic bond? A sigma bond. As drawn, yes, that is a sigma covalent 2-electron bond. What's wrong with that? Why does that make me mad? That's an ionic compound. They don't have covalent bonds. This doesn't exist. You show me this, God, I want to just fail you for the whole semester. No, I don't. I really don't. But it does strike a nerve. Because you learn that in Gen Chem. You learn that sodium hydroxide is ionic. Ionic compounds don't have covalent bonds. You cannot show the dissociation of an ion. Electron arrow pushing. I'm going to say that again. Electron arrow pushing does not show the dissociation of ionic compounds. So you just start with it dissociated. That's what you do. Same thing up here. There's often a sodium or a potassium ion that balances tert-butoxide. It's kind of fun to see it written out because it looks like TBU, okay. But there is no covalent bond. The potassium can honestly be ignored because it's just spectating the reaction. It's just there to balance charge. So I don't show it often. You're welcome to show it. Deal?
Why doesn't it make NABR?
It does. I've just shown it in its dissociated form. That is NABR. Sodium bromide solution. Any questions so far on the mechanism, the regiochemistry, the type of base? E2 reactions are considered stereospecific. They have to go through antiplanar elimination. That means that the hydrogen, the beta hydrogen, and the leaving group halogen have to be oriented opposite of each other at the time of reaction.
Real quick, between the Zaitsev and the anti-Zaitsev, they both eat protein. What's the difference? Just the location of that double bond.
Correct. Yeah. Anti-Zaitsev goes for the less substituted alpha hydrogen. Zaitsev goes for the most substituted. I say alpha hydrogen. Sorry. Least substituted beta hydrogen. most substituted beta hydrogen. Zaitsev is a regiochemistry term, much like how Markovnikov is a regiochemistry term. There's two things that we can look at for this antiplanar geometry. If we're looking at a Newman projection, that means that we're looking at a leaving group and a beta hydrogen that are oriented in the same plane and opposite of each other. And if that's true on just a normal Newman projection, then that has to also be true on a chair conformation Newman projection. The leaving group and the beta hydrogen have to be anti to each other. So when it comes to linear chains, you just have to make sure that your leaving group and your beta hydrogen have opposite stereochemistry, one wedged, one dashed. And if they're not, then in a chain, you just have to rotate to a new conformation where they do have opposite stereochemistry. In a ring, that leaving group must be in a specific position in order for E2 to occur. Where is that position on the ring? Axial. See, it all comes back. I taught you chair conformations for a reason. You can't understand E2 without knowing how chairs take up space. Must be axial. And by how I've drawn it, it must always be up axial, correct? No. Down axial groups also have anti-hydrogen positions. But equatorial groups do not have anti-hydrogen positions, anti-beta hydrogens. If a halogen were here in an equatorial position, what's anti it is a carbon with its hydrogens, not a beta hydrogen. So a couple of examples here. Let's start with linear chains. I'm going to draw two diastereomers. Because E2 is stereospecific, the products that form are stereoselective. An EZ isomer is formed in these two products. Only one can be formed selectively. Notice in the top structure that the most substituted beta hydrogen is already anti. Bromine is wedged, beta hydrogen is dashed. This top structure is already in the appropriate configuration for E2. So when the elimination occurs, I get this trans E alkene. Can someone explain to me why I don't have a wedged methyl group anymore? It's not chiral is true. It doesn't matter is a little bit true.
Is it because there's no more stereo because you took the hydrogen, so it's doesn't have sp3 hydride?
It's not sp3 anymore. It's not tetrahedral. It's sp2. I do take points off for showing that alkene product with a wedged methyl group, because you are forgetting one of the most fundamental parts of the chemistry, which is hybridization and molecular geometry. The correct answer is flat. The incorrect answer has a wedge on it. Is that okay with you guys? It's sp2. That methyl group is no longer chiral. That methyl group no longer has stereochemistry. In this second reaction, the diastereomer, that same beta hydrogen is no longer anti to the leaving group, which means this conformation will not work. Here's a shortcut on what I do to predict that structure. Flatten the bond line chain, much like we did in the top, and recognize that it's the wrong stereoisomer, and flip two of the groups. That's the shorthand. Just flatten it down into an alkene and flip two of the groups to get the stereoisomer of the alkene. The long way around it is to show the conformational change. And there's two ways you can do this. You can either show the rotation of the bromine and methyl, or you can show the rotation of the hydrogen and methyl. And that's what I'm going to do. I'm going to keep the bromine in the same place so it stays wedged. But I'm going to take this ethyl chain, and instead of being zigzagged, I'm going to make it zig-zig. And when I do that, the dashed CH3 becomes a wedged CH3, and the wedged hydrogen becomes a dashed hydrogen. Now what I can do is just flatten that carbon chain and put in the alkene. But you remember what I said before, where you could just draw the carbon chain as you see it and swap two of the groups to get its stereoisomer? Swap the methyl and the ethyl, and you get its stereoisomer. Because E2 is stereospecific, because it only reacts antiplanar, these products are stereoselective. And I just want to compare these to a more simple reaction with a compound like this. This compound does have an anti-periplanar beta hydrogen in this conformation. And this compound has an anti-periplanar hydrogen in its other conformation. So the E2 reaction is still stereospecific. It only reacts with the antiplanar hydrogen, but it's not stereoselective. This bottom reaction is able to make two stereoisomers. But just because it makes two doesn't mean it makes them equally. What would be the major product of this reaction? Which one forms more readily? The transalkene, because the transalkene is more stable. So to clarify, only product, stereoselective. Both products may form, but this is the one that forms to the largest amount. This is the major elimination product.
second. How is the hydrogen able to stay dashed?
The hydrogen doesn't stay dashed. This dashed hydrogen is wedged here. And the wedged hydrogen here is this dashed hydrogen. So maybe it would help, Hayden, if I drew this hydrogen as blue, and it's blue down here as well. And I draw this hydrogen as red, and it's red down here as well. And the product that we form here is from eliminating that red hydrogen. And the product that we form up here is from eliminating that blue hydrogen. But now my color scheme is really off. Does that help?
Yeah.
There are two hydrogens. Only one is anti to the bromine at any given time. They're always opposite. Questions? Earlier I told you guys that small bases are Zaitsev if possible. This is methoxide, the conjugate base of methanol. Methoxide is a small base. That means it prefers the Zaitsev elimination. Can you tell me the degree of substitution of my alpha carbon? He said, yeah, I can. Secondary alpha. So of my two beta positions, which one is more substituted? Which one would give me the Zaitsev elimination? The tertiary beta on the top. So let's look at that tertiary beta hydrogen. Oh, shoot. Can I run a Zaitsev elimination with this small base? Can't I just rotate it into a different conformation? In rings, I can do two chair flips, but I can never take a group that is wedged and dashed and rotate them to be both wedged or both dashed or whatever. That leading group, iodine, and that beta hydrogen in red are locked in a syn relationship, not anti. But there is an anti-hydrogen here. So that's where the base has to go to, because this reaction is stereospecific, and this red hydrogen doesn't align. That is not the most substituted alkene possible, but it's the only alkene that E2 can form. So, I want you guys to give me a reagent that I can use to form this alkene. I want you to think about it. Don't say it out loud yet, but when you are ready with an answer that you think might work, just raise your hand. Okay, I got 1, 2, and a half, maybe a quarter. It's a double handshake. If you don't think you know an exact molecule, 3.5. Maybe give a classification of molecule. Ideas? Okay. A large base, like tert butoxide? Well, tert butoxide is going to look for this hydrogen anyways. Water. Or to give you another example of a small base, and to keep it similar to this, methanol. A weak base is not stereospecific in its elimination. A weak base will cause a carbocation to form first. That carbocation is going to rearrange to this tertiary position anyways, and then run elimination. E1 is not stereoselective. Not only can E1 give you structural rearrangements, but they can give you elimination that E2 can't give. All right, I want to look at this example. I want to bring us back to some of our chair confirmation days. I'm sorry, I'm going to make a slight modification here. I'm going to make these 1,4 to each other. 1 tert butyl, 4 chloro. Oh no, I don't think that's what I want. Yeah. See, I'm messing up because I'm trying to give a specific example off the top of my head. Don't do that. All right, we're going to keep it the same. 1 tert butyl, 3 chloro, cyclohexane. Which conformation, the highest energy or the lowest energy conformation, is reactive to E2 elimination? To find out, we have to sketch them. We have to find the conformation where the halogen is axial, correct? And then we have to decide whether that is the highest energy conformation or the lowest energy conformation. And if you're someone that works with chair conformations a lot, then there are tips and tricks and rules that you can look for, like the every other rule about what will be axial and what will be equatorial. But if you don't work with chair conformations a lot, if you're a normal person, then you have to kind of sketch it out to convince yourself. This is chiral, which means it does matter which way I relate the groups on my chair conformations. They have to conserve the same rotational direction. But it doesn't matter where I place them, just as long as they're related the same. So I'm going to put chlorine here. And because this is an up carbon and chlorine is an up group, chlorine will take on up axial.
Oh, I thought you were saying when you switched.
When you flip it, you're right, you are right. And I'm going to sketch in the down equatorial hydrogen to clarify what my positions are. And then going counterclockwise to position 3, I get another up carbon with an up tert butyl group. And I can draw in this down equatorial hydrogen. Who feels like we need to draw the second chair conformation to make an assessment about which is the higher or lower energy level? Why?
We already know that this one, well, we know they're both going to flip to equatorial,
Mm-hmm.
and we know that axial is higher energy.
So without drawing the second one, we know that the second one will have less axial groups and will be a lower energy conformation. If you want to see it, you can. On a down carbon, you have an up equatorial chlorine, and on a down carbon, you have an up equatorial tert-butyl. Lower energy. But remember, the question was, which conformation, the higher or lower energy, is reactive to E2? Why? Leaving group must be axial. When the leaving group is axial, so is the tert-butyl group, and that is the highest energy conformation. So for this molecule, the highest energy conformation is reactive to E2. Using that information, I want you guys to discuss with yourselves about this diastereomer. Does this diastereomer react more easily? Or does this diastereomer require more energy to react? If we mix these two diastereomers in a lab together, which of them would go through E2 elimination quicker? Talk amongst yourselves. See if you're all on the same page.
Yeah, we were saying that one of the maximum ones would have a higher energy.
You never have them go
I did it. Oh, wait, it's not.
Oh, yeah.
Which one reacts quicker? Out of these two diastereomers, which one goes through E2 elimination quicker? Okay, what did you guys decide? Which one reacts through E2 quicker? The first one that we worked with, or the second one, the diastereomer we didn't look at? I got split ideas, so can I get volunteers to explain?
I thought the first one would be faster because it's higher energy.
So this is a higher energy conformation, which means that in order for it to react, it needs to get up to this energy conformation. And who said the second one will react faster? Right. So here, with our first compound, this was our reactive conformation, high energy. And with our second compound, this was our reactive conformation, lower energy. This second compound is going to be in the lower energy form more often because it requires less energy to be there, which means that it is ready to react as soon as a base is added to it. But the first compound needs to be put into its higher energy conformation in order to react. Less of the compound is there at any given time. The second one reacts faster because the reactive form is the lower energy form.
Sure.
Which means it...
Could you also be you can also, because I know it doesn't have to be that arrangement, it can go the other way. Because if you put the form as an RS and you put only going down 1, 2, 3, it's going to both be able to axial up and down in the opposite directions. Does that mean another reason?
I'm not sure I quite understand. These are the two diastereomers that can exist. Well, no, that's not true. There are other diastereomers, but they're going to have the same energy levels. They'll just be enantiomers of each other. Okay, so let's say that you have these two reagents in your lab, and you mix them into a reaction flask. How much of the green reagent is in this conformation at room temperature? A small amount. It takes a lot of energy to get up into that conformation, and it doesn't take as much energy to go back down. So a larger amount of the green diastereomer is at this unreactive conformation at room temperature. What about the red diastereomer? This is more likely to be at the reactive conformation at room temperature. It requires more energy. Keep in mind, it actually doesn't take as much energy for the red conformation to get to its higher energy state. This chair has 2 axial groups in its high energy state. This only has 1 axial group at its high energy state. That's not as high of energy. But in its low energy state, this also has 1 axial group, whereas this guy in its low energy state has 0. So green is both the highest high energy and the lowest low energy, but red is reactive at its low energy state, which means without providing any external heat, red is ready to react. Green needs external energy input before it can react. Okay. Can I clarify that any better? Things that require less energy to form react faster because they are already in that lower energy state with less energy. Okay, I want to do another practice problem. It's similar to the one we looked at before, except now stereochemistry is relevant. We've got 3 different problems. One of them, I want to make 1-methyl S-tert-butyl, S5-tert-butyl 1-methyl cyclopentene. I got there eventually, thank you. The other one, I want to make 1-tert-butyl 2-methyl cyclopentene. And the last one, not given to us. We're going to find out what it is, but I want to get there making it with tert butoxide. Why don't you guys work with each other for a few minutes and try to decide what reagents can be useful in making these two compounds and what compound is made from this last reaction. I want to spend less than 5 minutes on this, so do what you can and collaborate if you can. I just wanted to intimidate. Are you thinking about regiochemistry? Are you thinking about stereochemistry? Are you thinking about the different classifications of bases that we have? Those are your 3 topics to consider: regiochemistry, stereochemistry, base type. Don't lose your stereo. Or just square. That's nice. This one is stereo selective. The beta hydrogen there is not anti. It's gonna do both. No. Oh, you're thinking for the one that turf butoxide makes? No, that's not it. Think about where your beta positions are. That's where turf butoxide will eliminate from.
Is this the right reagent pouch or possible?
Mm-hmm.
That's what I was thinking.
Sure. So then the question is, how does this form if there's sin?
That's
Yes. No, because this dash corner is a dash hydrogen pair. OH minus needs them to be anti. That works. Yes, that works. Dash line. Put this dash down there. All right. I'm sorry to cut you short, but we need to move on. Thinking about regiochemistry. This is a tertiary alpha carbon, which means there are 3 beta positions that could form an alkene. Here is a primary beta, secondary beta, and tertiary beta carbon. Tert-butoxide will go for which? Tert-butoxide goes for the least sterically strained, the least substituted. So tert-butoxide eliminates from the primary beta carbon. Does that change the stereochemistry at the tert-butyl group? No. But it does take that CH3 to a CH2. It removes that chlorine, and it creates this methylene group.
It's because there's, for like the CH or the methyl group, it's because it would have a dashed hydrogen, right?
That's true. There is a hydrogen on here that can be put into an anti-configuration from the chlorine. Absolutely. Okay, so tert-butoxide goes for that primary beta carbon, makes a methylene group. What compound would go for a secondary carbon then? Well, that's more Zaitsev than the primary carbon, but it's not as Zaitsev as taking this tertiary beta hydrogen. But this tertiary beta hydrogen is not anti to the leaving group. So a small, strong base cannot take this beta hydrogen. Then, the next most substituted position is here. So something like hydroxide or methoxide or ethoxide eliminates here. How then can we get this most substituted, tetra-substituted alkene? Can't be E2, has to be E1. So what's a good reagent? Water, methanol, ethanol. All of those work great. Okay. Fun times in elimination reactions. Time to move on.
So wait, would any of these not involve the alpha carbon?
All of them involve the alpha carbon. That's where the leaving group is.
Because which one was it earlier when you reacted it with? It was like a when you reacted it with.
I see. So the E1 that we had earlier had a carbocation rearrangement.
And that's when it shifts to not with the alpha carbon.
Yep. But this won't go through any carbocation rearrangements because the carbocation that forms will be tertiary.
Which is good enough.
That's going to be the most stable. All right. The next reaction that we will see with alkyl halides is substitution reactions. The generic form for our substitution carbon loses a bond to something, carbon gains a bond to something else. That something else is a nucleophile. That nucleophile is donating electrons. I know this might seem confusing, but not all nucleophiles are anions. Many of them are. The best nucleophiles are, but not all of them are. There are two types of substitution reactions. First order, nucleophilic substitution, SN1. We read it backwards. How many compounds does the rate determining step of SN1 depend on? 1. That's why it's first order. And in alkyl halides, that one compound is the alkyl halide because this goes through a carbocation intermediate. That's an important term in terms of regiochemistry because it means that we have the potential for carbocation rearrangements. It's also important in terms of stereochemistry because it means the nucleophile is attaching to the carbon from either the top face of the flat carbocation or the bottom face of the flat carbocation. That creates two different chiral configurations. So SN1 gives us what we call mixture of stereochemistry. So, first of all, the regiochemistry of SN1. Because it forms a carbocation, this has a preference for more substituted or resonance stabilized positions. SN1 prefers secondary carbons, tertiary carbons, allylic carbons, benzylic carbons, because those positions stabilize a carbocation the best. The stereochemistry chiral carbons form both R and S configurations. If it's the only chiral carbon, that's a racemic mixture of enantiomers. If there are other chiral carbons, then you get diastereomers that mix. If there are no chiral carbons, you would never know the difference. If there's an SN1, then there must be an SN2. Obviously, this is second order nucleophilic substitution. This does not have a carbocation intermediate. Things to know about the regiochemistry. It prefers less substituted and also allylic and benzylic positions. As it turns out, those conjugated places, allylic and benzylic places, they just stabilize intermediates. They lower activation energies. The stereochemistry is described as inversion of configuration. If the group that leaves was R, the new group is S. If the group that leaves was S, the new group is R. If it's not a chiral center, you wouldn't know the difference. So inversion of configuration, R to S or S to R, this is often referred to as a backside attack. It's actually a phenomenon we've seen already in the halogenation reactions. When a bromonium ring forms, when a halonium ring forms, the nucleophile attacks directly opposite of that ring, breaking that bond open. That's a backside attack that gives anti-configuration. This is a backside attack that gives inversion of configuration because all you're doing is swapping two groups. Now, in these reactions, nucleophiles are described in three ways. Nucleophiles can impact whether you go through SN1 or SN2. First, we'll look at weak nucleophiles. These are things that don't necessarily donate electrons well. Water, alcohol, those were our bases. But bases are things that donate their electrons to take a hydrogen. That is a nucleophile. The only difference here is they're donating their electrons to a carbon instead of a hydrogen. Also, some halogens, like chloride and fluoride, are considered weak nucleophiles. No, bromide and iodide are considered strong. Then we have strong nucleophiles. Of course, we see things like hydroxide, alkoxide, bromide, iodide. But we also see things like alkyne ions, these acetylide ions. Those are strong nucleophiles. They share their electrons well. Cyanide, which is nucleophilic from the carbon, because both carbon and nitrogen hold a lone pair in cyanide. But carbon is less electronegative, so carbon shares better. Carbon is a better nucleophile. Sulfides are good nucleophiles. That sulfur is willing to share its electrons with carbons. Okay, there was a weak nucleophile I don't use at all, if ever, or little, if ever, in my classes, but I do want to highlight it. There's a weak nucleophile in carboxylates. Even though carboxylates hold a negative charge, that negative charge is delocalized by resonance, so it's not very good at sharing its lone pair, but it can act as a nucleophile. The other compound that I actually like quite a bit is azide. Azide in 3- is a very useful reagent in organic synthesis and organometallic synthesis, because azide can react with alkynes through a copper catalyst in something that's called click chemistry. And they say that because the two groups, the azide and the alkyne, click together to form a ring. So this is a very useful reagent to have. The last category that we can describe here are the bulky nucleophiles. You're never going to believe it. It's just terbutoxide. So terbutoxide is not a good nucleophile, unlike all of the other RO minuses. So because of that, it can be considered weak, but it's not weak because it's bad at sharing its electrons. Maybe we could say it's a poor nucleophile. It's good at sharing its electrons. It's just not good at getting to highly substituted places because it brings a lot of steric strain with it. So I want you guys to realize that we have just created a list of a lot of the same reagents that acted as our bases, which means sometimes compounds can react with their reagent in both substitution and elimination mechanisms. So for example,
I live over in Mill Creek on Highland, and I can either take 39th all the way over to campus, or I can take 45th all the way over to campus, and I kind of meet in the same spot, well, at different ends of the building. But I'm starting from the same place, and I'm taking very similar routes to get to school, and I end up in slightly different parts of the campus, a little bit different. This is similar to how one reagent can react with the same compound to either give substitution or elimination. Same reagent, but different outcome. Yeah, maybe my analogy didn't make a lot of sense. So here's a table that helps me organize how different reagents and different alpha carbons are going to react differently. On the left-hand side, we're going to analyze regiochemistry. So this is methyl halides. Oops, I'm going to give some space for a top row here. Methyl halides, primary alkyl halides, secondary alkyl halides, and tertiary alkyl halides. There is no such thing as a quaternary alkyl halide. Across the top, we're going to create 4 categories of reagent. Those are reagents that are strong bases and strong nucleophiles, weak bases and strong nucleophiles, strong bases but weak nucleophiles, and weak bases and weak nucleophiles. And at each of these different regiochemistry markers, we're going to see what type of reaction, SN1, SN2, E1, or E2, or combinations of them, are expected. At a methyl halide, methyl bromide, methyl iodide, methyl chloride, you cannot run elimination because you do not have 2 carbons. And carbocations are incredibly high energy. They take a lot of energy to form. Plus, steric strain is low. So I want you to notice on this regiochemistry column, steric strain increases as you go down. That alpha carbon has more steric hindrance around it. But also as you go down, carbocation stability increases. So there is a trade-off between second-order reactions happening at low steric strain and first-order reactions happening at high carbocation stability. Second-order reactions do not take place where steric strain is high, and first-order reactions do not take place where carbocation stability is low. Carbocation stability, first order. Steric strain, second order. These are the 2 features of regiochemistry that first order and second order reactions depend on. I'm going to fill in some of these reagents. Strong base, strong nucleophile. Hydroxide, alkoxide, and carbon groups, like the acetylide ions. Keep in mind that acetylide still has a pKa around 25. That is a strong base. It's a stronger base than hydroxide. Weak base, strong nucleophile. These are the sulfides, cyanide, azide, and the halogens. I apologize for kind of shortcutting those a little bit. You want to put
HS minus, please do. You want to put Br minus, please do. These are things that donate their electrons well to carbon, but do not donate their electrons well to hydrogen. Strong base, weak nucleophile. This is terp butoxide. Weak base, weak nucleophile. These are things like water, alcohol, and our smaller halides. Where steric strain is low, where steric strain is low and carbocation stability is low, and where elimination is not possible, the only reaction that proceeds with any type of reagent is an SN2 mechanism. You will not form a carbocation, and you cannot eliminate. There's no beta hydrogen from a methyl halide. Where steric strain is low, but not zero, SN2 is still a favored pathway from almost every reagent. But primary carbons start to introduce steric strain. So terp butoxide splits its behavior between SN2 and E2. Primary carbons experience some steric strain, so terp butoxide just eliminates instead of trying to substitute. At secondary carbons, steric strain is increasing, but carbocation stability is also increasing. Things that do not want carbocations will either substitute if they're good nucleophiles or eliminate if they're good bases. Things that are not good at eliminating but are good at substituting, they still run SN2. And things that are bad at substituting but great at eliminating, terp butoxide selectively runs E2. And weak base, weak nucleophile, these are things that can't really fight the steric strain to substitute, but don't really care to eliminate either. So they split their behavior between SN1 and E1. And they'll do the same thing at our tertiary alkyl halide. They'll split their behavior between SN1 and E1. My strong base, that is a bad nucleophile, can't substitute where there's too much steric strain, so it runs elimination. My strong base, strong nucleophiles, these also have too much steric strain to substitute, but they're very good at elimination. And then there's this last one. At tertiary alkyl halides, steric strain is too high for second order substitution to occur. So things that are bad at being bases but really good at being nucleophiles can't be nucleophiles, but they also don't want to be bases. So I like to mark this as uncommon, but in reality, it's probably going to be a mixture of E1 and SN1 reactions. The thing is, you're just going to avoid that. You're not going to introduce a reagent that's not good at doing its job there. All right, I have taken us to time. What we're going to cover tomorrow is how, when there are mixtures of reactions, you can actually use temperature to control forming one or the other. We're also going to look at how alcohols react through elimination and substitution. It's much simpler. And we're going to look at one last type of reaction called the Diels-Alder.
So we've got a lot for us tomorrow. But trust me, if you can process what we did today with alkyl halides, tomorrow will be smooth sailing. Okay? I'll see you guys tomorrow.